Okay, so we're interested in the real and imaginary parts of complex numbers, as in if z is a complex number, which is to say z is an element of the complex set of complex numbers, then you can write z as x plus iy, where x and y are both real numbers. You can write z as a real number plus I times another real number. A real number x plus I times another real number. And those two numbers have terms. The real part of z is the x value, that x value, and the imaginary part of z is the y value. Now, this is an important point. So, for example, the real part, let's do this. The real part of 8 plus 7i is the number 8. The imaginary part of the number 8 plus 7i is the number 7. Okay, and this is an important thing not to get wrong. The imaginary part of a complex number is a real number. I know that seems weird. Okay, 7i is not the imaginary part of 8 plus 7i. 7 is the imaginary part of 8 plus 7i. And so sometimes that's written where if z is complex, then z equals the real part of z plus I times the imaginary part of z, and the real part of z and the imaginary part of z are both real. Yeah? I'm not very good at writing the Blackboard bold C, but if z is a complex number. Okay? Now, there's another idea here. I might just sort of shrink this slightly because that's kind of obvious from the definitions up there. But there's another idea here that's important. If z and w are both complex numbers, and z equals w, then the real part of z equals the real part of w, and the imaginary part of z equals the imaginary part of w. Now that's sort of seems odd to say. We haven't actually done a lot of work on the equality of complex numbers. Two complex numbers are equal given a few circumstances, but what it basically means is that 3 plus 4i can't be equal to 4 plus 3i or something else, that some other value. In order for the numbers to actually be equal, you need these parts to be equal, and you need these parts. You need the imaginary part and the real part and the imaginary parts to both be equal. As in, you can't write, 6 plus 8i as 6 plus something else I. Yeah? There's no other number here which will give you that equal relationship. You can write, obviously things like 3 plus 4i is a half times 6 plus 8i, but then the real part of the right-hand side is still 3, the real part of the right-hand side is still 4. You could write 3 plus 4i as I times negative 3i, let me get this right, plus 4. Okay, you could write it as I times 4 minus 3i, but that's just a trick, that in the sense that this here is the imaginary unit, but 4i is the imaginary half of the number. 4 is still the imaginary part of that right-hand side number. Yeah, this is a multiple of two complex numbers multiplied together. Yeah, the two complex numbers multiplied together. Let's just do a few examples, just to ease our way into the idea of real and complex parts. The real part of the number 7 is 7. The imaginary part of the number 7 is 0. Yeah? By the way, 7 is, technically speaking, a complex number in the sense that the set of complex numbers is a subset of the set of reals. We've talked about this before, and something that this book that we're using doesn't always consistently identify. The real part of the number 8i is 0. The imaginary part of the number 8i is the real number 8. Yeah? The real part of 3 plus I over I is a bit complicated to work out. I'm going to avoid the word complex, but the real part of 3 on I plus 1, and I think you can see that the real part of that is going to be 1, in that this is clearly going to be a complex number, but rather than skip ahead to the answer, let's actually do the work. So it's the real part of 1 plus 3i on negative 1, okay, when you multiply by I on I, and therefore you get the real part of 1 minus 3i, which is to say 1, yeah? That's basically all I needed to say, yeah? Good. By the way, this is probably important, that if z equals, if the real part of z, let's do this, if the real part of z is 0, then z is said to be imaginary. It's often written as purely imaginary, i.e., therefore 8i is imaginary, whereas 2 plus 8i is not imaginary, it's complex. And 2 is also not imaginary. 2 is real. Yeah? This is an important idea here, that for a number to be purely imaginary, it needs a real part of 0. For a number to be purely real, it needs an imaginary part of 0. Yeah? And any number which the combination of the two is complex, numbers that are purely imaginary also fit within the complex range. Numbers that are purely real also fit in the complex range, and complex numbers can include numbers that have non-zero real and imaginary parts. Okay, so what else did I want to hit here? Okay, box 8 is sort of obvious. We're familiar with the idea that if, so let's start with, given x and y are both real and z is x plus iy, the real part of z is x, the imaginary part of z is y, then z conjugate is written as x plus iy conjugate, which is x minus iy. Yeah, the conjugate is a number where you turn the imaginary part into its opposite. Instead of y, you use negative y here. Okay, so just say, therefore, what is a half times z plus z conjugate? You get a half times x plus iy plus x minus iy, which is a half of 2x, which is x, which is the real part of z. Okay, that's relatively obvious. That's that first idea here. To get the real part, you can add a number and its conjugate and halve it. Yeah. Also, you're interested in 1 on 2i z minus z conjugate. Well, why it's 1 on 2i will become clear in a minute. This is x plus iy minus x minus iy, which I think you can see is 2iy. 2i divided by 2y. 2i divided by 2y gives you 1. That's y, which is the imaginary part of z. That's what all this is saying here, is to find the imaginary part. You can subtract a conjugate from itself. You can subtract a conjugate from a number and then divide by 2i. Okay, that's a helpful maneuver in some examples. And I think that's basically what I wanted to do here. So it would be worthwhile doing an example or two from the book. I say we do 11D just quickly before I finish this video. Let's do 11D and maybe just a few examples in question 12. Maybe I'll do that in a separate video. This is exercise 1A, question 11D. Okay, so what's it asking? Express in the form x plus iy. They're basically asking you to find the real part and imaginary part of this complex number, which involves a bit of work. So we all love complex number arithmetic, but I promise you that the smart way to go here is to rationalize the denominator. I actually just noticed something which is a bit... I noticed clearly that this is negative 2 times that, which is not what a standard student would notice. So let's just continue with rationalizing the denominator. Sorry, not rationalizing, quite clearly. I'm sure you all picked up on that. We are realizing, we're changing the non-real denominator, it's a complex non-real number, and turning it into a real number by multiplying by its conjugate. Okay, so the top line here, the numerator is negative 8 times negative 2 is 16, minus 10i, minus 32i, plus 20i squared, which is minus 20, all over negative 2 squared is 4, minus 16 plus 16. Okay, up here, what have we got? 3 minus 6i plus 8i minus 16i squared, which is plus 16. 1 minus 2i times 1 plus 2i is 1 plus 4, or 1 minus 4i squared, which is 1 plus 4. Okay, then you end up with negative 4 minus 42i over 20 minus, well, you might make as a, just the minuses are making me uncomfortable, plus negative 19 minus 2i all over 5. And so then if we're taking the whole thing over 20, we've got negative 4 minus 76, is it? Minus 42 minus times 4, 8. Sorry, that minus 42i for 8i. Then if it's negative 4 and negative 50, is it negative 5 over 2i? Now that has answered the question. The question asks you, express in the form x plus I, y, where x and y are real. I've expressed in the form x plus I, y. The questions might ask you find x and y, or rather find the real and imaginary part. X is negative 4, y is negative 5 over 2. I might have made a mistake on the way there because it did seem to suggest that there was supposed to be an integer answer there. In any case, that is the process. If I've made a mistake, then that's great. Somebody pointed out to me. In question F, you're going to do something quite similar. You're trying to prove this question. I might as well also copy the question part of the question because it gives us the variables to put in. Given, it's about proving some results from conjugates. I've chopped off a y there. Given z equals x plus iy and w equals a plus ib, where a, b, x, y, and real, prove that. Okay, so i.e. the real number, the real part of z is x, the imaginary part of x is of z is y, the imaginary part of w is b, and the real part of w is a, because they're all real numbers. This is an important part of the question, that the coefficients, if you like, the real and imaginary parts are all real, obviously. So how do you prove that? Well, how do you prove anything which is an equality? You're just going to do left-hand side equals the conjugate of z divided by w. Now, how do you find the conjugate of something? You find the real and complex, the real imaginary parts, and you the real imaginary parts, and you take the imaginary part and make it negative. So we're looking for z, which is x plus iy over a plus ib. Just like the previous example, you're going to realize the denominator so you can then separate the real and imaginary parts, because you need the numerator, you need a real denominator to separate the real and imaginary parts. We've still got to take the, sorry, I should do it in purple. We're still looking for the conjugate of that answer. Okay, so then we've got ax plus aiy minus aib minus I squared by all over a squared minus I squared b squared, and then we're still finding the conjugate of that whole number, and so that's ax plus by plus I times ab minus ab. Okay, I made a mistake here. This is not right. This is xib minus xib. So I knew I made a mistake at the middle. I saw the next line. Ay minus xb all over a squared plus b squared. Yeah? Conjugate of that. How do you find the conjugate of that? Well, the real part is ax plus by over a squared plus b squared, and the imaginary part is plus this, yeah? So the conjugate is going to be minus ay minus xb over a squared plus b squared, all times I, and then I can write another line there if we like to just sort of flip the numerator, but we don't really need to because now we're interested in the right-hand side. The right-hand side is z conjugate over w conjugate, which is to say x minus iy over a minus ib. Conjugate of w is a minus ib. And then again, you're going to realize the denominator in much the same fashion. A plus ib times a plus, sorry, I was going to do that in green usually, wasn't I? Just to show that it was not part of that line, times, a plus ib over a minus ib. So that's what? Ax minus aiy plus xib minus I squared by all over a squared plus b squared, minus I squared b squared is plus b squared. So then we've got the real part is ax plus by over a squared plus b squared, and then we're going to do, we'll just write it as plus bx minus ay over a squared plus b squared, which equals the left-hand side. You can see here that that and that are the same thing if you take into account this minus here. Okay, so what's that saying? What's that saying? Mr. Horton's fond of these kinds of sayings, I'm sure you recall. This is a way of saying the conjugate of quotients equals the quotient of conjugates. Meaning, if you divide a pair of numbers and find their conjugate, it's the same as finding their conjugates and then dividing them. Yeah, it's exactly the kind of thing that we've been doing for a lot since the beginning of Year 11, where I commonly say the sum of squares is not the square of sums, but the product of squares is the square of products. You know, these sorts of things. Where you're doing two functions, you're adding and squaring, but if you do them in a different order, you get a different answer. But if you multiply and square, you get the same answer as if you square each and multiply. That's what that's saying here. Conjugate each and divide, you'll get the same answer as if you divide and then conjugate the result, or find the conjugate of the result. Conjugate is a funny verb. It's more in linguistics than in maths. Okay, so that's plenty to get on with. I might do a few more of those in response to some of your questions.